So, now we will discuss passive scalar turbulence. Okay. So, we have done the formalism. So, includes definition of flux, spectrum. So, 1D spectrum will be defined similarly, So, energy in a shell is 1D spectrum for theta. Okay. So, we look for spectrum E theta. Is it some power law or not power law, what properties? It turns out we can derive it quite nicely by what we studied so far. Okay, so I rewrite the equations. Okay, now, but it's quite so. Velocity field is exactly same as before, except that is Fu is not a function of theta, and we will assume that it is forcing only the large scale, active at large scales. Remember, so we had said stirring at large scale. Now, what about theta equation? So, u dot grad theta plus f theta. Okay. I will also assume f theta, but this also at large scale. If I do not put f theta, then it will decay by kappa. Right. If there is diffusivity and if I do not put f theta, it is decaying theta squared. So, we will assume f theta is at large scale and non-zero. So, it will induce a cascade of theta squared, which we discussed. Now, so it is exactly same set of equations, but I made an assumption that is Fu is independent of theta. So, that is why it is called passive. Okay. So, scalar energy flux which we already have. So, vector energy flux or velocity flux is same as before, but scalar energy flux will be. So, I am assuming steady state. Okay. So, d pi d theta by dk is f theta of k minus d theta of k, and the flux is usual definition, theta squared coming out of the sphere, rate of theta squared coming out of the sphere by nonlinear terms. Okay. Now, in the inertial range, we let this go to 0, and also this goes to 0 because this is active at large scale. So, if you look at k space k, so dissipation is active here and f theta is active here. So, the inertial range where both are absent, like Kolmogorov theory. So, I will say that d pi theta dk is 0, implies pi theta of k is constant. Okay, so, it is easy to derive. So, pi theta must be constant. Of course, it should be 0, but I assume that this is a sink, kappa is non-zero, supplied large scale, that generates a flux, and that is non-zero. If you force here in Fourier space and sink here, then there is a channel of energy transfer. Okay. So, pi theta is constant, I already derived from formula of variable energy flux, this formula. Okay. So, now what about spectrum? What can you say about the spectrum? So, E theta of k, this is what I am looking at, is dimension is theta squared by k. You agree? So, the integral of E theta k dk is theta squared. So, it has dimension of theta squared by k. Now, this can depend on what all? I will do dimensional analysis like Kolmogorov derivation in Fourier space. Okay. There are two derivations we have done so far, Kolmogorov 4/5 law, which was lot of mathematics real space, but in Fourier space it was proving first that pi u is constant, then apply dimensional analysis. So, now E theta k can depend on various things. So, it can depend on k, local wave number, and flux, right. So, how many fluxes are there now? There are 2 fluxes, right. So, there is pi u and pi theta. So, there are 3 of them. So, we have, instead of pi u and k for hydrodynamics, we have 3 of them now, pi theta. So, I am going to call it alpha, beta, gamma. Okay. Now, we need to determine alpha, beta, gamma. So, this dimension, so what is dimension of pi theta, by the way? It is theta squared by time, injection of rate of injection of theta squared. So, this will be theta squared by time. So, we need to put all the dimensions properly. So, this theta squared by k means theta squared times L. This is theta squared by time times alpha. K to the gamma means L to the power minus gamma. Pi u is a squared by t. So, there is a u squared by t, sorry, u squared by t. So, this is L squared by t cube. So, this is L squared 2 beta by t 3 beta. So, now we can figure out what all the 3 quantities. By the theta has come as a new quantity, okay. So, that is why I can determine all 3. So, with L and T it would not have been possible, but theta has come as new. So, now we can easily see that alpha is 1, right. From here 2 and 2 alpha, alpha is 1. Beta is from here. So, alpha plus 3 beta must be 0. So, beta is minus 1 by 3, and now gamma you can figure out. So, 1 plus 1 equal to 2 beta minus gamma. So, gamma equal to 2 beta minus 1 is minus 5 by 3, right. So, my E theta of k is pi theta pi u minus 1/3 k minus 5/3. So, this is a formula for E theta. So, it is 5/3 again, but now my level of the spectrum depends on both pi u and pi theta, and one exponent is 1, other one is minus 1/3. Together gives you 2/3. So, that is interesting, but pi theta and pi u are different quantities. Okay. Now, this is spectrum for passive scalar. It turns out it works quite nicely. People have verified it in experiments and simulations, and I will not, I mean, there are lots of literature. Okay. So, you can look at some papers by P. K. Young, and there is a constant in front, is called Ubukow-Korsin constant. CURR, what is Korsin spelling? CURR, no, 2R? Korsin. So, this constant. Okay. Now, so we have constant. So, if you force at large scale, then pi theta is constant and spectrum is minus 5/3. So, this is the phenomenology for scalar turbulence. We get this k minus 5/3, pi theta, pi u minus 1/3, but there is one catch, is that we assume that the spectrum is independent of forcing at large scale and dissipation mechanism. So, this assumption which you should remember, assumption independent of large scale forcing and dissipation mechanism or diffusion mechanism. Okay. So, nu and kappa do not come into it, and also how you force it don't come into it. Okay. So, this is another assumption which is assumed here to derive phi third. If you do not force theta square, then it will be decaying theta square. Okay. And decaying turbulence also is expected to be, if your energy is large, then initially phi third, then it will go into some different power law, but it will decay in time. Okay. But that I will not discuss, the decaying part I will not discuss. Is there any question on this? Okay. So, we can also define quickly what is the inertial dissipation range. So, that means this formula is what I described in the last slide, is only for the inertial range. Now, can we combine both? Is there a formula which can do both? Now, velocity field will be what? What is a good candidate for you for the velocity field? So, Pauw's formula should be good, no? We done. So since it is same, no, when passive scalar velocity field is exactly same as hydro, no change. So, Pauw's formula is good, and it seems to work reasonably well. Okay, this one. So, this pi u and pi theta, pi u and EU. What about pi theta and E theta? Would you want to make some guess? So, I still want to make pi theta. So, I will give you the how I should do it. So, in the inertial dissipation range, f theta is 0. So, in this wave number I am in this range. So, the dissipation is strong here, but it is everywhere, it's strong in large k. By the way, k squared E theta minus 2 kappa. So, E theta is non-zero, that means dissipation is there even for low wave numbers, but is weaker, it becomes stronger at k squared. Okay. So, now we can write d pi by dk theta is minus 2 kappa k squared E theta of k. These are definition. F theta is 0, so it follows from variable energy flux. Now, I make the Pauw-Ansatz. What is Pauw-Ansatz? E theta of k by pi theta of k is independent of nu and kappa. So, I will say there now there is another diffusion coefficient. So, it is independent of both nu and kappa. So, it function only of k, epsilon u and epsilon theta, and epsilon theta must be same as pi theta. Yes, because if you can derive it exactly like what it is. If it integrate from here to there, then energy injection rate must be equal to the total dissipation rate. So, pi theta, by the way, this derivation you should do yourself. This you can do it from first principles. Pi theta approximately epsilon theta. And epsilon theta is always, well, I can't say, epsilon theta approximately equal, not quite equal. Okay. Now, the function of these three. So, by dimensional analysis, what should I can derive it, but I already know the formula. So, we derived it in the last slide. So, it is k Uberkov-Korsin constant, then epsilon. So, pi theta is going to come as epsilon theta here. So, that should go away, minus 1/3 and k minus phi third, right. E theta is pi theta pi u minus 1/3 k minus phi third. So, this is what should be, right. I mean, you can do it by divisional analysis, but this is what is going to come. Substitute it there. So, what will I get? D pi theta by dk is minus 2 kappa k squared k Uberkov-Korsin epsilon u minus 1/3 k minus phi third and pi theta. So, I get a function 1D ODE, first order ODE of pi theta. I can solve it. Now, this minus phi third and k squared gives you 1/3. If you integrate it, I will get k 4/3. In fact, the derivation is exactly same as what we did for hydro. Okay. So, this is how we can derive, and so I expect this instead of Kolmogorov I will get this, and instead of Kd I will get Kc, which depends on kappa rather than nu. and E theta will be this, and Kc is the Kolmogorov constant, Kolmogorov wave number for theta. So, these where my theta squared spectrum is like this, no, minus 5/3, then it should steepen, and at some point theta squared is no more fluid. So, this is Kc. Kc is not here, so please remember Kc is not here. I call it Kdi in my new book. In old book it was Kd, Kc, but now, so there is a ratio is factor 2, but Kd and Kc are different. Okay. So, Kc is where fluid velocity or fluid the theta squared is losing the fluid meaning, and you can now this is epsilon u. Interestingly, epsilon theta does not come in formula for Kc, epsilon u comes. This derivation is interesting. Epsilon theta does not come. So, what is Kc by Kd? Is nu by kappa. Now, I forgot to say this ratio is called Schmidt number for passive scalar. For buoyancy driven flows it is called Prandtl number, but for all the passive scalar literature you will find it is called Schmidt number, okay, and is 3/4. Is a useful formula which comes many ways. Okay. So, this is how we can generalize, and we have not tested it, and I am not sure no, this needs to be tested whether it will work for passive scalar. Okay. Is that clear? I mean, so this is a conjecture, whether it works or not we can figure out from experiments. Numerical experiment is easiest. So, these are the equations for pi theta, pi u, and pi theta, E theta, and we did in the past EU and pi u, but these are applicable when both of them are 5/3, EU and E theta, right. So, there will be EU as well on this, EU, and this E theta. So, both are 5/3, and then this part we are focusing on the dissipative range. So, this formula is both dissipation and inertia, but the assumption that both are 5/3 assumes that both Reynolds number and Peclet number are much bigger than 1. So, there are regimes when Reynolds may be order 1 small and Peclet may be large. So, laminar flow, but for which the theta part is turbulent, right. So, there are regimes which I am not covering here, but you can look at in the notes. Re much less Re this one and Peclet much bigger than 1, or other way around, Re much bigger than 1, Peclet less than equal to 1, or both less than 1. These regimes I have not covered in this lectures. Okay. So, this you have to see the notes because I will not cover it. Now, structure function. So, we can do exactly same thing like Kolmogorov, and this was done by Yaglom first. We are all Russian groups, 1949. So, instead of 4/5 it is 4/3, and this proof is simpler. So, you can have a look at the proof. It is minus 4/3 epsilon theta L, but it is following the same lines, but it is simpler because it is scalar. So, we do not have third rank. So, the tensors become simpler with theta. We define S theta, third order, for which there is exact relation. So, S theta I have not written here, the definition is, so there are 2 points R and R plus L. So, difference is L. So, theta prime minus theta whole squared. So, scalar value at R plus L minus scalar value at R square, and delta u. So, u prime minus u parallel. Parallel means I take the component along L dot L cap, or we had notation of n. So, this is the component of the velocity fields along the L direction. So, u prime minus u parallel take the projection. So, I will say n. So, this quantity is third order structure function and this goes as this object minus 4/3 epsilon theta, dissipation rate of scalar quantity. Okay. So, now what is giver and what is the receiver for this? So, from this you can make interpretation. No? So, here this is the mediator, right, because u is the mediator. So, and both receiver and giver are here, one of them is receiver, one of them is giver, but it is a cumulative. So, in fact, this is receiver as well as giver, one of them is giver, one of them is receiver. Okay. If I take the divergence of this, that is supposed to be T theta, that is equal to flux. Okay. The derivation you will find that you have to take the divergence to equate it to the flux with some prefactors. So, the divergence will kill L. Okay. So, the point is, even in real space we can interpret as a something is mediator, something is a giver and something is a receiver. So, this is a beautiful way to interpret these formulas. Okay. And it also works for MHD, which I will try to explain when I do MHD. So, this is minus 4/3 epsilon theta L. Now, when you compare with Kolmogorov K41 that was minus 4/5. So, which is delta u square times delta u dot n, right. So, it was all three of them, there was minus 4/5 epsilon u L. So, this L is proportional to the distance between the 2 points. Okay. So, these formulas are very similar, the prefactor is only different, minus 4/3 and minus 4/5. One of them is dissipation of scalar, other one is with dissipation of u squared. Okay. This has been verified by P.K. Young. There is a paper in 2005, at least one paper I know, but there could be more paper. Okay. So, we stop. Thank you.